So let's solve some problems involving potential, but potential now for a single charge. Okay, so as we know, as we saw, the potential for a single charge is given by K, the constant, Q, which is the charge that is involved, and R. R is the distance from that charge. In this equation, the sign of the charge is important. We have to take this into account, if it's Q positive or if it's Q negative. And as you have in these slides, how we can plot the potential versus R. If the charge is positive, this potential is positive, very close to the particle. If this R is very small, this potential is very large. As we move away from the particle, this potential is going to become smaller and smaller. If the charge is negative, the potential, since we care about the sign of this Q, the potential will be negative. Initially, the magnitude very large, but a minus value. So very close to the charge is the magnitude is very large, but negative. And as we move away from the particle, it becomes smaller and smaller. Anyway, all this to say that in this equation, the sign of the charge has to be written. Okay, so we can have positive potential or negative potential, and the potential is a scalar. It's different from the electric field, is different from the force and other quantities which were vectors. For the electric field, the magnitude of the electric field when I have a single charge is K Q R squared. This is just the magnitude, and this is always a positive value. The direction of the electric field, well, then we have to talk about angles. It will depend on the problem itself. In the case of potential for a single charge, this is the equation, and this is not a vector, this is a scalar. So this is a scalar, and this is a scalar that can be positive or negative depending on the charge. This plus and minus, they have nothing to do with direction. They only have to do with the fact that I had either positive charge or a negative charge. Okay, so this is important. Now let's go for the problem. So the fact that this potential is a scalar makes life much easier. Now we don't need to think about vectors, we don't need to think about directions. So we just add and subtract numbers. Makes solving problems with potential is much easier than solving problems with electric field or force. Okay, so let's see this first problem here. They want to know what is the potential, okay, the electric potential at this point, this distance, for these two cases. One case is the case where the particle is positive 20 microcoulomb. The other case is a charge that is negative minus 20 microcoulomb. How are we going to do this? Very simple. Part A, the positive charge, well, you have to put the value of K. Remember, K is something like close to 9, 10 to 9. Q, we have the Q here, 20. Okay, now careful. We do care about the sign. So for the positive one, I'm putting there the positive sign, 20, 10 to minus 6, because we are talking about microcoulomb. And then the distance from the charge, 0.5. So you put these numbers there, you're going to get that the potential for that positive charge is 3.6 10 to 5 volts. This is a positive value because we are dealing with a positive charge. What do we get for the negative charge? Well, it's again the same thing, 9, 10 to 9. Now careful, negative charge, we do care about the sign, we put it here, okay? And then the rest is the same. And we have also the distance, and we are going to get the same number, but careful, we have to remember to put here this minus sign. So the potential for the negative charge is going to be minus 3.6 10 to 5 volts. Okay, so in this sense, this is very different from the problems for electric field. I'm going to repeat. In the problems for electric field, this equation that we have, k q over r squared, we don't care about the sign of the q, because this equation just gives us the magnitude of this electric field. It's just going to be the number associated with it. The direction will come from the problem by playing with vectors. In the case, okay, so this is for electric field, we do not write the sign of the Q. When we are talking about potential, then yes, we do write the sign of the change. Okay, so this is very important. Okay, so, but the problem here, this 17.4, was very simple. Let's go to the next problem, 17.5. And now in this problem, we are talking about the question of the promised work. So what is the question? What minimum work must be done by an external force to bring a charge of this magnitude from a great distance away to a certain point, 0.5, from a charge q. Okay, so what is the scenario here in this problem? We have a little q positive, little q that is positive, 3 microcoulomb, very far away from another q, a big q, which is also positive. This q is 20 microcoulomb. So this this little q is positive. It's very far away from this big q 20. And but it doesn't want to get close to this big q. What we are going to do is we are going to exert a force, an external force. So we are going to do external work. Yeah? We are going to be injecting energy to bring this particle from far away to close to a distance here that is 0.5 meters, 0.5 meters away from this big Q. Okay, so the little q does not want to get any close to the big Q. It's as far as it can be. To bring it close to the big Q, we have to exert an external force. We have to inject energy to overcome the barrier, to bring this little q close to the big Q. So let's remind ourselves of what we saw before for the equation of work. We said that the equation for the work done by the electric force, as the particle is moving in its natural motion, now going from high potential to low potential. Now, so this is the work done by the electric force in the direction of decreasing the potential energy. This work is Q minus Q, final potential minus initial potential. So this work done by the electric force is positive, because for the negative charge, this q is minus, and we get then a positive value. For the positive charge, this q is positive, but the positive charge goes naturally from high potential to low potential. So for the positive charge, this is negative, and again we get positive work. Okay, so this is work done by the electric force in this natural tendency of the particle, which is to lose potential energy. What we are doing in this problem is not that. We don't have force done by the electric force to decrease the potential energy. No. We have an external force that is carrying this little charge closer to the big charge, which is then adding potential energy to this little q, because this little q does not want to be close to the big Q. Okay, so this work that we have here is external work, injecting energy also. And what is this equation for this external work? Plus Q. Plus Q, and then we are going to put the final potential minus the initial potential. Okay? Does it make sense? Look, the final potential for this little q will be very large. Will be very large, and so this difference here will be positive. huh? And the Q is positive, I'll have positive work, as indeed I'm injecting energy into the system. So this is the equation that we have to do. So all this discussion just to talk about the equation that we have to do. Now we just need to put the numbers there. What are the numbers? Well, the little q we know is 3 10 to minus 6 coulomb. What is going to be the, now here we go for the potential difference. What is going to be the final V? The final V is the V given by this big Q. Okay, so this final V is going to be K Q over R. What is this R? This 0.5. Okay, so this is the potential. This final V is the potential given by the big Q. Okay, what is the initial? Well, when the charge, the little charge, was very, very far away from the big Q, it didn't feel the big Q. No? The potential for this big Q far, far away is practically zero. How do I know that this is zero? Let's go back to this plot. So we are talking about the potential of this big Q. Very close to it, it has a large potential. But if I go infinitely away from this Q, you see, infinitely away, the potential becomes zero. If I put here a huge number, this potential will become very close to zero. Okay, so that's how we solve the problem. To get this external work that we have to do, that this external force has to do to bring our little q from far away to close to this big Q. Now, so the big Q creates around it a potential. Very, very far away from it, this potential is just zero, but close to it, this potential exists. And by putting these numbers there, we are going to get the work that we have to do, 1.08 joules. Energy that is injected, work that is done by an external force, positive, because we are injecting energy.